We have also a third type of relation. We have also a second type of decoder models that we can use. And these are called position models. So on this, we have three types that we would like to look at. We have rescale, we have decimal, and we have complex. So we start from rescale, which is the most famous one. It is able to represent different, similar to rotate, it is able to represent different logical patterns. The way it works is that it learns embeddings for ZH, ZT, and R tau, but the embedding that it learns for the relation R tau is not a vector anymore, and it's a matrix. And the idea is that, if you remember, we were dealing with decoders that were dot product decoders when we were learning those essentially embeddings. This is just an extension of that. We are saying that we have a vector ZH multiplied by a matrix R tau, and that's multiplied by a matrix ZT. And then we will say that this is going to give us the score that we are going to use for reconstruction of our knowledge graph. So there is, when you basically have a matrix in between, what this learns is that each element, I and j, of this embedding matrix for the relation is learning how element I of embedding for head node is interacting with element j of the embedding for the tail node. So there's one problem with this, and that problem is computational complexity, computational expense. So the problem is that we have our R tau this time, which is not a vector anymore, it's a matrix, so it's a larger amount of computation needed to learn the embeddings. And if you think about it, knowledge graphs are not small. They're basically, their number of edges and nodes in the billions. There are different types, there are hundreds of thousands different relation types. So one thing that is very important for these models is that they should be scalable, and we should be able to use these models in order to apply them for larger and larger matrices. So another model that we can use is called dist-mult. Dist-mult is used, it is essentially a similar definition, except for that the matrix R now is diagonal. So it has zeros everywhere else. So basically, we can write that as just a vector, and we can write this as element-wise multiplication of three embeddings, right? So, or if you want to write it in the matrix format, you can just define RT as a D by D matrix, which is diagonal. So it's basically that both are the same. So this type, as basically we reviewed before, we had dot product decoders when we were dealing with learning node embeddings. Now this type of decoder is generalizing that by introducing a relational embedding when computing the dot product. So it's a element-wise product of basically three embeddings, and we have a sum over those, so that we get the score, basically for a particular relation between two entities. So let's see if this dist-mult can infer on different relational patterns. So on symmetry, we write this equation down. We say that what is the output for the decoder given embedding for entity H, embedding for the tail entity, and the embedding for relational, basically edge type tau. So we write that here, and we see that we can, this is a commutative relation, so we can just basically swap the places of ZH and ZT, and it's still the same, right? So if I do that, I'm gonna get essentially FD of ZT tau ZH, right? So for both of these, we have the same score. So we would be able to essentially simulate or basically infer on symmetric type of relations between the entities using this model. All right, how about anti-symmetry? Unfortunately, we can't, because this is commutative and it only can handle the symmetries. So it won't be able to basically deal with an anti-symmetry relation, because given the tau, it means that both ways are always correct. So nothing of that sort can happen. Now, for inverse, we can't. The problem with inverse is that if I write these down for two different essentially entity types, I will basically get equations that have ZH, ZT on both sides, and therefore all elements of the embedding for the relation type tau1 and tau2 are going to be the same. So essentially, I will have the same embeddings for both basically for both relation types tau1 and tau2. So that's not acceptable, because we want different embeddings that represent different type of relations. So next thing basically is complex, which is a model that from its name you can guess that it is incorporating it is basically defining embeddings in the complex space, in the complex vector space. And by that, it is helping the DISMALT to be able to represent anti-symmetric relations. Now, the equation is as following. We still are using essentially a sum or element-wise product of these three embeddings, with the difference that three differences. First of all, we are using a conjugate basically of the tail embedding. Conjugate meaning that in the complex number, the real part is the same. The imaginary part is going to be multiplied by a -1. So the second thing that we do here is that we are applying we're only taking the real part of the summation, and we don't consider the imaginary part for our score. So, and essentially, yeah, so those two. So that's it. So this is how we define it, and all ZH and RT and ZT are defined in the complex domain on a d-dimensional complex domain. So let's write down the basically this equation to see if it can represent symmetric relations. So if I write this equation, I can take the real inside the summation, right? And then because if we basically consider that the imaginary part of our relation basically embedding is 0, then we can take that out of this real, right? Because it doesn't have an imaginary part. We take it out, and then we can simply swap the place of the conjugate for these two head and tail, basically tail and entity embeddings, right? So I do that. I again reintroduce R inside this equation, and I take that RE basically out of the summation, and I see that I get the output for df of ZT tau ZH. So I am able to, if I start from basically the head entity and go with relation type tau to ZT, I would be able to also represent the other way around. So I would be able to represent symmetric relations here. Can we do inverse? Yes. I'm not going to go over it, but we would be able to do that using basically by defining one relation embedding as a complex conjugate of the other relation embedding. But still, it has the problem of representing essentially a composition type of relation, composition of two relations that will result in a third relation. So just to review upon what we have covered for knowledge graphs, we defined knowledge graphs. We said that knowledge graphs can represent a collection of facts starting from one node entity, one entity. We say there's a relation between this entity and another entity. So for example, someone is someone's son, that means that these two people are the entities and the relationship son is the relation between these two entities. So we can use graph structures to represent all these. And this is basically being used for a lot of applications in computer science. For instance, when you search some query on Google, it is the way that it uses, it is the algorithm that it uses to respond to you, especially when you see the knowledge panels. Then we said that we want to basically complete these graphs in many cases because the information we have, usually they have missing links, a lot of them. For instance, we said that in Freebase, there are a lot of peoples as entities, and for 71% of them, we don't know the place of birth. So we want to be able to predict this, for instance, we have the cities and entities, we have people as entities, and we want to be able to predict their place of birth. So that was one example. So knowledge graph completion are approaches that help us to complete knowledge graphs. And also now our basically information about the world is evolving as well. So that's another point that we can use knowledge graph completion approaches to tackle. We said that we are taking a shallow embedding approach to basically to address knowledge graph completion problem. And in these problems, we studied 6 types of decoders categorized in 2 categories. We had translational models that included trans-E, trans-R, and rotate-E. And the essence of this was that relations are defined as translations in some space. Now, this translation can be just, in a Euclidean space, or it can be defined in a complex space. So then we again went to the basically tensor decomposition type of decoders. We studied rescale. We said that it is expensive, but it is able to cover all type of relationships. This small and complex are 2 other models that are used most often in basically papers and literature, but they have the problems of their own.